Okay, hello everyone. I hope that you had a nice half term. We're going to continue with graphs and we're moving on to a real difficult topic called velocity time graph. So previously we've done distance time. Now we're going to look at velocity time graphs. I'm going to hopefully go over some definitions to try and make things a little bit clearer. Just a quick recap. Have a think about, we're going to use this skill later, what these two shapes are. Hopefully we'll recognise that they are trapeziums. They are trapeziums because they are quadrilaterals, i.e. four-sided shapes, and they have one pair, if I denote it like this, of parallel sides. This would also be, we'd traditionally see it like this, but this would also be a trapezium because it is a quadrilateral with one pair of parallel sides. These are obviously not parallel. Okay, to work out the area of a trapezium, well, let's just make up some numbers. So if I had this was 4 centimeters, this was 6 centimeters, and then if I knew that this height straight up, i.e. the perpendicular height, was, let's just say 3 centimeters. Sorry, I shouldn't have done that different. 3 centimeters. Then to work out the area of a trapezium, I add together my parallel sides, multiply it by the perpendicular height, and divide by 2. 10 times 3 is 30, divide by 2 would give me an area of 15 centimeters squared. Right, if I had, let's call this one 5 centimeters, this one 7 centimeters. In this case, if they meet at, if those two lines there, if those two angles, apologies, were 90 degrees, then this would act as the perpendicular height. Let's call that 4 centimeters. So if I add together my parallel sides, multiply by the perpendicular height and divide by 2. Let's have a think about that. 12 times 4 is 48. 48 divided by 2 would give me 24 centimeters squared in this case. We're going to use that skill later. Right. First off, so I was going to write that. A recap of distance time graphs. So we did really well on that. I've been really impressed with the progress that we're making, but you're going to see a range of different types of graph. And you need to read the question carefully and then look at the question carefully. I know this one here would be a distance time graph because the y-axis would tell me it was dealing with distance. Let's just call that distance in meters and this time in seconds. This is a distance time graph because its distance is being plotted versus time. So if I had this, as we've recapped a couple of times, a typical journey might look something like this. So someone has moved, and if I wanted to work out the speed of this bit here, then I would work out the gradient. I know that they've come to rest and then they've returned home at a constant speed again. Straight lines on a distance time graph denote a constant speed. If they're horizontal, it denotes that they are at rest or not moving. So just so we've got it clear in our head, let's just do one example with this. Let's say that for this journey, they covered 20 meters in, say, 5 seconds. Yeah. So the speed of this bit would simply be 20 divided by 5. 20 meters divided by 5 seconds. So at that point, they're moving at a constant speed because it's a straight line of 4 meters per second. Important for our notes, the gradient of a distance time graph tells us the speed. Right, and that's true of these bits as well because the gradient here would be 0. Yeah. Right, I've touched on this in the last video, but just so we're clear with these things, these are real technical things that we need to fully understand. If, let's say I call from left to right the positive direction, often the case, yeah? Think about graphs. So if this is a positive direction, let's say something is moving in this direction with a speed of 10 meters per second. That thing could go back the other way and its speed would still be 10 meters per second, yeah? Because speed does not care about direction. You can go whatever direction you want, the speed is just the speed. The difference between, let's call that speed. The difference between speed and velocity is this. If I call this the positive direction, that's a bad arrow, and it moves with a speed of 10 meters per second, I could also say that it moves with a velocity of 10 meters per second. If, however, the particle then moves back this way, or the thing, let's call it, moves back this way at 10 meters per second, its velocity would be negative 10 meters per second. And that's the distinction. Velocity cares about direction. Speed doesn't. That's the distinction between speed and velocity, guys. So if I'm talking about speed, I don't care. Velocity does care. And it's very important that you stipulate, you consider what direction it's moving in. Right. Here's a velocity time graph that I've just made. And I'll just make that clear. So let me just label these axes. This is the velocity. So it's speed with a direction. The direction is important. And I'm just going to say that the unit of that is meters per second. And this is the time. And let's just call that seconds. For the sake of this one, let's just make up some values. So let's say that this one here was moving at a speed of 20 meters per second at that point. And let's say over a period of 4 seconds, let's say that they then moved at a constant speed for this period. And let's call this time here 12. Right, let's have a think about this journey. Well, this time, look, it's velocity, it's not distance. The velocity is increasing with respect to time. The change in velocity is acceleration. So that's a real difficult thing to get your head around. Something could be going at 100 miles an hour. The acceleration could be 0 if its speed doesn't change. If it's just going at 100 miles per hour the whole time, its acceleration is 0 because the speed is not changing. Acceleration is the change in speed. Yeah? So let's write that. Acceleration is the change in speed, or let's call it velocity, with respect to time. Now, the next bit is this. To work out the acceleration from a velocity time graph, it is the gradient of it. So the gradient of a velocity time graph gives us the acceleration. Right, so that's one thing and another separate point underneath. So let's just look at this. Assuming that, I shouldn't assume, I should put that in there. I'm going to say that this thing is accelerated, and it's accelerating because its velocity is increasing with respect to time. This is accelerated from 0 to 20 meters per second. In order to work out the acceleration for the first 4 seconds, I would work out the gradient. The gradient of the velocity time graph gives us the acceleration. So I know it's gone 20 up and 4 across. For this first part of the journey, it has moved at, well, this unit's a bit confusing. It's 20 meters per second. So I'm going to call that, 20 divided by 4, which is 5. And then I've got meters per second divided by second. The units for this acceleration is therefore 5 meters per second squared. Let's think about what that means. That's saying for every second that passes, the speed increases by a further 5 meters per second. It's quite confusing, that, yeah? But this is the important thing to remember. Gradient of velocity time graph gives us the acceleration. Well, the gradient is here. It's just going to be 0, isn't it? It's definitely not at rest. It's moving at 20 meters per second, but because the velocity is not increasing or decreasing, it is moving at a constant acceleration. Right. Therefore, if we have this bit here, so this is moving at 0 meters per second squared. And then finally, we have this last bit of the journey. Here, the gradient is negative. It's gone up 20, or down 20, I should say, apologies, and then over 2. But I know that this is velocity, so direction matters, just as direction matters with acceleration. So this is going to have an acceleration of negative 10 meters per second squared, or I could say a deceleration of 10 meters per second squared. Yeah? So that's how we work out acceleration from a velocity time graph. Couple of things we can do with velocity time graphs though. And the other thing, let's take this wonderful diagram. The other thing we can do is work out, paste. The other thing we can do is work out the distance that this thing has covered. I'm just going to tidy this up slightly. So let's get rid of this. Whereas it was obvious before, the distance covered, because the distance was just given to us in the actual graph itself on a distance time graph, this one's a bit more confusing. On this one, let's write this down, the area under a distance time graph, sorry, this is a velocity time graph, tells us the distance covered. Right, well, let's have a look at this. I could, if I wanted to, split this up. So I'm going to work out the distance underneath this and draw an incredibly poor triangle. So we have one triangle here. Let's label what we have on that. I know that the time covered, that much is 4, and it goes up 20. I have this rectangular shape here. And if I think about that between 10 and 4, between 10 and 4 would mean that the length across the bottom would be 6, because that's the difference between the two numbers, and again it goes up by 20. And then we finally have one more shape here. And this shape is also a triangle. Which has a base of, the difference between 10 and 12 and 10 is 2 across the bottom, and then it goes up by 20. The area underneath the velocity time graph tells us the distance. Well, let's work out the area of each of these things. 20 base times perpendicular height divided by 2, or 4 times 20 divided by 2 is going to give me 40 meters. So in fact, I've worked out for the first 4 seconds, it moved 40 meters. Okay, so my next one is going to be 20 times 6. And that's going to give me 120 meters. And then my final bit is going to be 20 times 2, base times height, or height times base, divided by 2 is going to give me 20 meters. Therefore, in total, all I need to do is just add all those things together. 40 add 20 is 60, plus 120 should be 180 meters in total. Now, if I wanted to be real clever, I might have instead said that all of this shape is just a trapezium. And then I'd work out the area of that trapezium. You don't have to use this method. Just showing you it because you're such a capable class that I feel it's interesting to look at both methods. So I know the length across all of the bottom is 12. I know that this bit, the other parallel side, the difference between 10 and 4 is 6. And I know that the perpendicular height is 20. So let's just work those things out. Add together the parallel sides. Multiply it by the perpendicular height. And divide by 2. Lo and behold, it gives me exactly the same answer. Yeah? Let's just recap that, guys. If we've got a velocity time graph and I'm asked to work out the acceleration is the gradient of the velocity time graph. Gradient of velocity time graph is acceleration. The area under the velocity time graph tells us the distance covered. So I can work out two things from a velocity time graph. Have a think about that. Then I've given you 3 questions to do. I'm then going to explain those 3 questions in a separate video. Keep up the hard work. See you later. Bye.